Hey guys, BuildZoid here, and today we're going to be talking about what is, safe operating temperatures for VRMs, because I've seen a few posts on Reddit and some comments from people basically either freaking out about temperatures that weren't high enough to freak out about, or just people wanting to know what exactly would be safe, because apparently I've not made it, well, I probably haven't made it, like, very clear at any point in time. So today I'm going to try make it clear. Unfortunately, I can't just give you a flat number because VRMs are made up of many different components, and temperatures don't, there are temperatures at which your components will basically instantly fail. But as you decrease the temperature, all that really happens is your reliability kind of improves. So, it's that's why you have capacitors that are rated for 5,000 hours versus 2,000 hours or 10,000 hours if you're going for, higher ratings. And then you have capacitors rated for higher temperatures, lower temperatures, you get a range. And so it's not as simple as saying, okay, if you run it at 105 degrees, you're fine. Well, with the capacitor, you're fine for the next 5,000 hours. But at the end of those 5,000 hours, that capacitor is still not going to explode. That's not what aluminum polymers do. So, it's not as simple as saying if you run at this temperature, you're going to end up with XYZ result. There are certainly temperatures that, will cause instantaneous failures. But when it comes to what's actually what would be okay, you're kind of looking at sort of you kind of need to balance it a bit. So then, let's get into it. Now, this image right here is, of course, not a motherboard. It's an RX 480. I've from Tech Power Up's review of the reference RX 480. And I grabbed this image because this is the most convenient VRM layout that I could get to highlight all of the components in. Now, admittedly, all of these capacitors are very much part of the VRM. The reason why I generally ignore them is because there's a lot more capacitors in this VRM than what you can see right here. Technically speaking, even these guys around the GPU core are probably part of the vCore VRM, as in they're hanging out on the vCore power plane. So they experience the voltage off of vCore. But anyway, let's talk about temperatures. So I guess let's start with the components that you don't need to care about, and then work our way down in terms of temperature tolerances. You don't need to care about inductors. It is very much possible to electrically overload an inductor, but basically the only if your VRM is running hot enough to harm the inductors, which are basically just a bit of copper wire going through a powder metal core or around a powder metal core and then encased in a powder metal, there's many ways to construct an inductor, but generally it's going to be some wire and some combination of powdered metal core. So these, they're gonna, if you get to a temperature high enough to damage these, everything else in the VRM is probably dead or about to die in the next couple seconds. So you don't need to worry about inductors aging from temperature. They do slightly derate, their saturation current capability goes down as they run at higher and higher temperatures, but that doesn't break the inductor, that breaks everything after it and before it. So basically, the inductors, saturation current basically just means once you hit that point, the inductor the inductance of the inductor falls off a cliff, and it starts being less an inductor and more a piece of just wire. And that naturally means that it gets really bad at converting 12-volt bursts into an actual lower DC voltage, and you start getting really, really unstable VRM output. Your VRM efficiency also tends to go to hell when that happens. So, but it's still not going to break the inductor, it's just going to break everything else. So you don't have to worry about the inductors overheating. You do have to worry about electrical overload on those. It's also possible to, exceed the average current capability of the inductor without exceeding the saturation current. And then the inductor will basically just get so hot that it'll break. But, again, that's an electrical overload. It's not like having the inductor sit at 125 degrees is going to harm it, or 150 degrees is going to harm it. If you overload it, then it's just going to keep climbing up in temperature until it breaks, which is basically the problem that you need to worry about. So you know, and then it's not about your VRM being at a high temperature, then it's about your VRM just kind of thermally running away on you, because the temperature is just going to keep climbing until it stops working. So that's that scenario. So inductors, those are out of the way. Next, we get on to the MOSFETs and the drivers. And I'm going to put these together because they're both semiconductor devices and they both have very similar temperature tolerances. So then, this is an RX 480. This MOSFET right here is an MDU 1511, which is why I have this data sheet right here. And, you know, this is kind of your bog standard power MOSFET from Magnachip, but most MOSFETs actually come with the exact same ratings. It is rated for 150 degrees Celsius for both, and, oh, damn it. I'm still not used to the new PDF viewer. But anyway, so junction and storage temperature are both limited to 150, as well as minus 55. And basically the reason why even the storage temperature is limited to 150 is that above 150, the actual doping of the silicon starts to degrade just from being hot. So you literally, like, if you took these MOSFETs and put them in an oven at 200 degrees Celsius for, say, a week, by the end of that week, most of them probably wouldn't work. Actually, maybe all of them wouldn't work. Okay, so you really, really, really can't run MOSFETs above that 150 degrees Celsius mark. And that is junction temperature, that's not external temperature. So basically, if you measure the VRM temperature, say, with a temperature sensor sitting somewhere around here, which would be like a reasonable place to place it, because that's going to be the hottest area of the VRM, that's still going to be cooler than what's actually the temperature of the inside of the MOSFET, which is what this temperature limit is referring to. That's the junction temperature. So that internal temperature has like every MOSFET data sheet has a description, like a indicator for the like relationship of the external temperature of the MOSFET to the internal temperature of the MOSFET. And basically here we can see that thermal resistance junction to case is 1.6 degrees per watt. Basically, that means if one of these MOSFETs is producing 1 watt of heat, and we measure on the outside of the MOSFET that it's at 120 degrees Celsius, then internally it's at 121 degrees, 121.6 degrees Celsius. Now, this is actually a very, very low thermal resistance, which makes these MOSFETs pretty high temperature tolerant, as in, like, if the VRM was at 120, then their internals wouldn't be that much warmer. But there's other MOSFETs out there, like, say, this is the MOSFET off of a MSI X470 Gaming Plus board. This thing has a lot more thermal resistance. This thing comes in with a thermal resistance of 3.8 degrees per watt, junction to case. It also has the same 150 degrees junction and storage temperature. So same sort of thermal tolerance. So, you know, but much more thermal resistance. So basically this means that your VRM is not okay if it's running at 150. Because if it's running at 150 on a temperature sensor sitting outside the MOSFETs, then the insides of the MOSFETs are definitely above 150, and that's not okay. So you don't want to run them that hot. So that's sort of the junction temperature, but because you also have this thermal resistance, I would generally recommend, like, I would already be concerned about most VRMs if they were hitting 140 or even 130 degrees Celsius. Like, that would already be a very concerning temperature range to be in, because they're, like, this 3.8, really not that bad. It can get as bad as, say, this thing, which is the 4C10N. A very popular high-side MOSFET for cheap motherboards and GPUs. This thing has an absolutely trash thermal resistance of 5.3 degrees per watt. So basically, so you get the idea. If you push 2 degrees, 2 watts of heat out of one of these MOSFETs, you're looking at a 10.6 degree increase against the external temperature. So that, like, at 140, the junction would still be above 150. So basically, 140 degrees, I would just consider unsafe in general. Okay, like, not okay. 130, also, I wouldn't really consider that an okay temperature for MOSFETs to run at, because, like, that's hot. That's really, really hot. And there's other things than the MOSFETs there that you need to worry about. Plus, funnily enough, even though all of these MOSFETs have listed the junction temperature and storage temperature as 150, if you actually look at parts specifically designed for power supply applications, like, say, this, which this is a... Oops, why is it... Bleh. This is what I get for trying to record this video over and over again. All the data sheets end up on the wrong pages. But this is a CSD 87350. This is a really, really popular dual NFET, or power block, as Texas Instruments likes to call it. But literally, if you look at the actual circuit diagram, it's two FETs glued together. So this is a dual NFET. And this is meant specifically for basically VRM applications because it solves the whole, like, it's two of the, like, it basically takes those two parts and combines them into one. So this is generally, this thing is by TI, meant to handle 40 amps output. This is very popular on, well, was very popular on Z170, Z270, Z370. I think it's actually still popular on Z370 boards. It was very popular on X370 boards. There was a lot of motherboards that use this thing. Some GPUs used it. Very, very popular part. And this, you know, if we go through the thermal data for this thing, you can see that our storage temperature and operating junction temperature are, again, 150 degrees Celsius, right? So that's still 150. But if we scroll down here with recommended operating temperatures, so what they would recommend you run these at so that they last as long as possible, the junction temperature is actually just 125. So it's not like if you exceed 150, they expect these things to degrade very, very rapidly. If you want these to last as a very long time, you want to run them at 125. And if we look at, say, a 3553 here, which is a really, like, a lot of motherboards use this, a lot of GPUs use this. This is a 40 amp power stage from International Rectifier. Very, very, very popular component. Right here, 40 amp power stage. So if we scroll down to this, lots of boards use this, lots of GPUs use this. You have, again, the same kind of situation where maximum junction temperature is 150. But maximum like recommended operating junction temperature is 125 again. And again, this thing comes with a thermal resistance right here of 2.5 degrees per watt. Because if I'm not mistaken, this thing does not integrate a temperature readout internally. So for these, you actually can't measure their internal temperature. And you're relying on a VRM, like a temperature sensor sitting somewhere near to these power stages. So again, you know, if you measure that the external temperature, like the temperature of the VRM is 120, and one of these power stages, if we scroll down here, then we have a nice graph of the power output. You know, you're pushing 20 amps through one of these power stages, it'll produce about 2.4 watts of heat right there. So at 20 amps through one of these power stages, 2.4 watts of heat times the 2.5 watts thermal resistance, and you end up in you end up with something around 6 degrees higher temperatures on the inside of the MOSFET compared to the external temperature. So if the VRM was at 120, then internally they're at 126. So that's your power stages, and now let's cover the drivers. So these specifically right here, these are CHL8510s. Very popular high-end driver IC, and it's this one. Also comes under the label 3537, but generally you'll find it CHL8510, and you can identify it because there's literally just 8510 written on top of it. But these are, again, the same thing as all the power stages and the MOSFETs. 150, you know, for junction operating temperature. Recommended temperature is 125, right? So for this reason, because all of these, your drivers are recommended operating temperature of 125, your power stages have a recommended operating temperature of 125. I'd imagine that if MOSFETs got like a recommended temperature, it would also be 125 relative to the 150 that everything out, like, because everything is spec'd for the same max junction, and then you get the 125 for the parts that are actually meant for power, for specifically for VRMs. Everything, all of those always end up getting a recommended junction temperature of 125 for longevity. Because of this, you'll also notice that most motherboards that implement an over temperature feature will implement an over temperature that kicks in between 125 degrees Celsius and 105. 105 is on, like, I think Asus puts that on some boards where it's like a really low temperature that it kicks in at. But Gigabyte, for example, consistently just has an over temperature that kicks in at 125 degrees Celsius. And this is why. Because if you're measuring 125 degrees Celsius external temperature, then the internal temperature of most of your power components is probably quite a lot higher. Still not completely, still not absolutely unsafe, but it's already starting to get into the situation where you're exceeding the recommended temperature for long-term longevity. So that's why when you have OTP, it's generally set to 125. It's also set to 125 because you have inside, like, crammed between the MOSFETs, you have multi-layer ceramic capacitors, and these are generally going to be made out of X7R rated materials. So X7R is a temperature rating from minus 55 degrees all the way up to 125 degrees. Now, admittedly, multi-layer ceramics, basically, if you exceed their maximum operating temperature, their voltage tolerance gets worse. So you can't run, like, if you bought a 30 volt X7R capacitor, then that means that, it would be safe up to, say, 28 volts or even 30 volts, but it's generally recommended that you derate them a bit. So if you derate it a bit, you go 28 volts at 125. Well, if you start exceeding 125, that capacitor goes from being okay for 28 volts to being okay for, say, 20, depending, or 12, or even lower. Like, the higher the temperature, the less voltage you can apply, because the electrical insulation, the electrical resistance of the actual capacitor internally of the capacitor gets worse and worse as it gets hot. So you run the risk of basically just punching voltage straight through the capacitor and it ending up a short circuit. So those, and on GPUs, the typical choice of multi-layer ceramic capacitor is X7R. So you're going to be looking at a pretty, that's why generally if there is an OTP, then it's set at 125, because yes, it probably wouldn't immediately die at 150. It's not ideal to run it at 150, at all. It's definitely not a good idea to try run long-term at 150. So 125 is sort of treated as the cutoff temperature for all of the safety features. And 125 would still not be what I would consider an ideal temperature to run your VRM at, just because, so your MOSFETs would be fine, your multi-layer ceramics next to the MOSFETs would be fine, but these capacitors right here and these capacitors right here won't be fine with that whatsoever. And this guy also, because these are all probably, well, I'm not sure specifically on the RX 480 if they're aluminum polymer capacitors, but they probably all are aluminum polymers. And the thing about aluminum polymers is that they generally come rated to 105 degrees Celsius, and then you get different flavors of like 2,000 hours, 5,000 hours, 10,000 hours, and 12,000 hours on motherboards. Like ASRock uses some 12,000 hours rated parts. Asus has some boards with 10,000 hours rated parts. But your sort of cheap generic motherboard, or even some of your other high-end motherboards, will just use 5,000 hours rated capacitors. A lot of the no identifiable label capacitors on GPUs will be rated for like 2,000 hours, and these all degrade at high temperatures. So here's a good example of basically what you're looking at in terms of degradation. This curve right here. Now, this is admittedly from Panasonic for Panasonic's aluminum polymer capacitors, because Panasonic has the nicest little graphic I could find, because all the other manufacturers, it's like these guys don't have a graphic at all. They're basically just like, oh yeah, you can lose as much as 20% of your capacitance, which is like a good indicator, but this is not super useful. So, and they don't show what happens at higher and higher temperatures. So you can see here that at 105 degrees, this is with a 2,000 hours rated capacitor. After 2,000 hours, it loses almost 10% of its capacitance. Then if you look at, and then, at higher temperatures, the degradation gets a lot worse very, very quickly. So at 155 degrees, you're going to lose almost 20% of your capacitance in like 10 hours. So if your VRM is going over 150, you are really screwed. Now, the good news is that since the capacitors are actually far away from all the really hot MOSFETs, at least the output capacitors are, and luckily for you, the input capacitors aren't quite as important as the output ones. You can get away with some of these guys missing. If a lot of these stop working, then you're kind of screwed. So, So these, these will end up running hotter because they're much closer to the actual MOSFETs which produce all of the heat. But these capacitors generally especially on motherboards, what I've found is that, if you measure the temperature, say here, then the temperature over here is going to be about 10 degrees lower. So if the VRM is at 115, that's when the capacitors will be at like 105. Or if the VRM is at 105, then the capacitors are at like 95. So you get this nice little temperature gap. Obviously, this temperature gap will get closer as the temperature of the MOSFETs gets closer to ambient. So if like the MOSFETs were at 60, then the capacitors would probably be around 58. Because at that point, there's, there's very little temperature. Like, you can't, there's a floor for how cool all of the components in the VRM can get. So, yeah, basically, at the higher temperatures, you're going to be looking at around a 10-degree difference between what the VRM is at and the capacitors are at. And the thing is, you need to just, be aware that they'll degrade. They don't cause catastrophic failure, which is the sort of the good news. Like, as you can see, basically after 5,000, like after 2,000 hours, you just lose almost 10% of your capacitance. And here with these, after 5,000 hours, you can lose as much as 20% of your capacitance and pick up some extra 50% ESR. So basically what happens to aluminum polymer capacitors is they don't go catastrophic failure. And there's actually, do I have that paper here? Yeah, here. So this is from Nichicon and their statement on the main failure mode of their FP series capacitors. So those are really, like, these are what you find on like most high-end motherboards are going to be FP series Nichicon capacitors, and those are aluminum polymers as well. And the main failure mode of the FP cap is open mode. So basically the capacitor stops being a capacitor. It's like it's not there. It's not going to short circuit and explode on you. It's not going to catch fire. It's not going to, cause any catastrophic damage. It's also not going to be very visible when the capacitors fail. Basically, the only way to check that you have bad capacitors is that you'd measure the output of the VRM with an oscilloscope. That would be the only way to tell that there's actually a problem with aluminum polymer capacitors. I also had a paper from NASA, though I guess I put that one away, where they tested like a whole bunch of different capacitor manufacturers, and they intentionally reverse bias the capacitors, so, and then dumped 20 amps through every single one of them, and all the, like, no catastrophic failures, like no explosions, no fire. The capacitors did at that point get some discoloration just because they ran so much power through them, but it wasn't like they would actually, like, you won't see, like, it won't take down the VRM. What it will do is that since your capacitor loses, like, over time, your capacitor loses capacitance and it gains ESR, what ends up happening is the capacitor gets less good at cleaning up the output ripple of your VRM and, maintaining voltage levels. Basically, the goal of a capacitor in a VRM is to make sure that the voltage doesn't deviate too much from what you're trying to hit. And so essentially what you'd have in a, if you have a VRM running, then the output is going to look something like, say, this when you have brand new capacitors, right? You get like a squiggle like this, and software isn't going to pick up that squiggle. And after, say, 10,000 hours at 105 degrees, so with significant capacitor degradation, you're going to have a squiggle that looks like this, right? So this is obviously a bigger squiggle than that one. And the problem that's going to cause is if, let's say you're running a very, like, when you first get your motherboard and you set up an overclock, then basically what you're doing is that your CPU is stable at this minimum voltage right here. And after 10,000 hours, your minimum voltage is no longer, that, it's this. And your CPU may not be stable at these lower points. So after 10,000 hours, you might find that before, your very fine-tuned overclock, which was like 5 millivolts away from crashing, well, now your voltage ripple on the output of the VRM is 5 or 10 millivolts higher. So your minimum voltage is about 5 millivolts lower, let's say, and now you're crashing. So it won't cause a catastrophic failure, but you may find that after some time, you're going to lose stability. And and the longer you run at higher temperatures, the less, the worse the voltage output of your VRM is going to get. And software will not pick this up because that squiggle at the scale I drew it, you're looking at something like a couple nanoseconds between each of those spikes. So your software is not going to pick up on that. Your software, basically, software voltage readings takes an average that looks like basically like that line, right? And so you're going to see, like here, you're going to see an average that looks like that. Here, you're going to see an average that looks exactly the same, except here you have more noise, like noise imposed on top of the DC voltage. Whereas here you have less. And that noise is going to cause the instability. And that noise is normally removed by all of your capacitors, except if the capacitors increase in ESR over time and lose capacitance over time, they get worse at doing their job of removing that noise, and your overclock may become unstable. If your capacitors degrade enough, hard enough for long enough, you can get to the point where even at stock settings, you're not going to be stable because the capacitors are just completely shot and your voltage regulation is just crap. But you find that kind of scenario on, say, like old GPUs where, those GPUs are like 10 plus years or older. Like really old graphics cards, which are just horrifically unstable. Oftentimes you'll find that they had bad capacitors, but we're talking about hardware that's like several years old in order to not be able to run stock. But if you're overclocking and you dial in an overclock, which is very, very close to being unstable, then, after 5 years of heavy video encoding workloads on a craptacular VRM that runs very, very hot with very bad cooling, you might find that, after 2 years or 3 years, your overclock is now unstable. And it'll be because basically your VRM degraded. And power supplies actually, main system power supplies have the same, they undergo the same process. They'll also degrade over time. Admittedly, a lot of the top-end power supplies come with ridiculously long warranties because they're designed with just way overkill out of the box. So, after 10 years of degradation, their voltage output is still going to be bloody great. But if you have a crappy VRM that's like a 3-phase, and then most of its bulk filtering capacitance disappears, well, with a 3-phase, you really needed those capacitors on that output. So you end up with garbage voltage regulation. But it's not going to cause a catastrophic failure. It ultimately, you really do need to run that VRM for 5,000 hours at that 105 degrees on the capacitors, which basically means if the VRM right here was at 105, then these caps are at like 95. And if we look at, say, Panasonic's data sheet here for how much, longer their capacitors are expected to last at lower temperatures, you can see that going from 105 on a 2,000 hours rated capacitors to 95 makes it last 6,000 hours. So, you'll get the same amount of degradation in basically 3 times the time period. So if you're if you're just gaming or something, which this would really, for gamers, this basically only applies to GPUs because GPUs are the only thing where the VRM really runs that hot. And then the other thing is that stock voltages on all hardware are ridiculously high, as everybody likes to point out. But you can undervolt Vegas and RX 480s and 580s and 570s, and you can undervolt pretty much everything. You can undervolt CPUs, you can undervolt everything. The reason why you can undervolt everything is that there's a certain amount of margin built into the stock voltages to accommodate for things like the VRM being, degraded after 3 or 4 or 5 years, or the craptacular motherboards that some of this hardware ends up running on, and bad power supplies and different temperatures, operating temperatures. So there's a lot of error margin basically built into the stock voltage, which would accommodate for certain amounts of VRM degradation. You can also find oftentimes that if you this is something I've seen on a few GPUs with SMD polymer capacitors that come in the CAN radial the CAN package, but with the SMD mounting system. Those I've seen a few of those where they were not soldered properly to the board, so they just fall off when somebody takes the heatsink off, which is really weird. But I've seen a few of those cases, and it's the card will still run fine if the capacitor falls off like that, and it'll run fine because capacitors are heavily redundant oftentimes, and then because you also have that voltage margin in your stock voltage, it may affect overclocking, which is basically the main issue. So yeah, and you'd need to rack up like several thousand hours at a very high temperature to run into these effects. So for that reason, 105 degrees on the VRM, I still wouldn't worry about. 110, I still wouldn't worry about because your capacitors are still going to be around, say, 100 or 100, like they're still not going to be at 105 because they don't actually produce all the heat. The heat is all produced by the MOSFETs, and then, well, capacitors do produce some of their own heat because of the current going in and out of them, but capacitors run hot because of the heat produced by the MOSFETs getting to them, rather than because they produce a lot of heat on their own. So, yeah, that's kind of that. So this running at 105 is fine. This running at 110, I'd still consider it fine. If you're gaming, then you don't have to worry about your mother. Like unless you were gaming for like 12 hours every day, I don't think you have much to worry about, right? Because let's say you did game for 12 hours every day. So 12 times 365, okay, so you might actually wear out you might wear out your GPU, right? Your GPU's VRM might wear out. That also depends if the GPU even needed all of the capacitors it came with. And also because depending on what voltage you run the capacitors at relative to what they're rated for, how much ripple current they actually have to handle, they'll last a bit longer. So you don't low hundreds, really not a reason for concern unless you are talking about something that runs 24/7. If you're running something 24/7, then I would start to, want to have the VRM at say 95 or 85 degrees Celsius. But if you're looking at something that runs, just 4 hours a day, like if you have a GPU and you game on it for 4 hours a day, and it also depends on what kind of game you're playing. Like if you're not playing Crysis every day or Battlefield or, something 3D, very graphically intensive, that puts the card at full load, you don't have to worry about it so much. If you're just playing indie games, then it's just like the card doesn't care. It's not gonna get hot. It's not doing any work. So, low hundreds, definitely not concerning unless you're running them 105 to 100, 100 to 115 degrees Celsius, perfectly fine, unless you're running it for 24/7 applications or 12 hours a day applications. But for that kind of scenario, you'd probably be looking at video rendering or some kind of, rendering workload. You're not gaming unless I get maybe full-time live streamers would run into issues with this kind of thing. But otherwise, you don't need to worry about this. And then if you're gaming on motherboards, then you really don't have to worry. Motherboards under gaming workloads, the VRMs really don't get hot. It's really just, video encoding, 3D rendering, large multi-core, workloads are what you'd have to worry about for your VRM temperatures. So, yeah, that's kind of that. Now, on the flip side, just because it's fine for the VRM to run at 105, 110, 115 degrees Celsius doesn't mean I'm going to not complain when a motherboard comes in with a craptacular heatsink that makes it run at 107. Okay? Because it's just I realize the heatsink is sufficient, but I'm 110% sure you could have come up with a better heatsink that cost just as much as the one the motherboard came with regardless, and it could have run cooler, and that would have made it last longer. There's no reason that, there's nothing wrong with making the VRM run better, right? So, and I'm not gonna just because the temperature is okay doesn't mean it's a good thing. Also, the other thing is that when I do my VRM thermal tests, I test at 25 degrees ambient. So if at 25 degrees ambient I have a VRM hitting 110, then it's okay, so if we go to a hotter climate, that VRM is going to be hitting 120. And at that point it's okay, well, now we kind of have a problem. Right? Because 120 on the VRM is, that starts seriously, you start exceeding that 105 degree temperature rating for the capacitors at that point. And that's a problem. So, Yeah. Then again, if you're just stress testing, then I wouldn't care about VRM temperatures. If you're setting up a gaming build and you're doing your stress test with like Prime 95 and the VRM is crap and it just it hits 125 degrees, then really the only problem with that is that it'll trip over. Like on a good motherboard, it should trip over temperature protection. And when that happens, what I'm going to say is just put a fan on the VRM, run your stress test with the fan on the VRM. Once your stress test is done, take the fan off and set yourself no, you don't even need to set yourself a temperature alert, because your motherboard's going to shut down when it overheats, or it's going to start to thermal throttle when it starts overheating. So you don't need to worry about you don't need to worry about that, because your motherboard has a safety feature. What is concerning is motherboards that don't have over temperature protection and also still have crap VRM cooling, because those motherboards is like, you can't even really like I wouldn't trust one of those motherboards to not catch fire under some freak accident scenario, right? Because if the motherboard is shutting down when you're running Prime 95 because the VRM is getting too hot, well, it's preventing the VRM from dying, so it's doing its job, right? Like that's the main thing, is we don't want the VRM to prematurely die on us, and that happens when the MOSFETs exceed 100, like start going close to 150, right? That's where you really start running the risk of killing the VRM. So if you're stress testing, is basically just make sure that the motherboard doesn't, trip over temperature protection, so that your stress test is valid. Because if the CPU is throttling, then you're not stress testing. If the system shuts down after 30 minutes of Prime because the VRM overheated, you're not stress testing. If the motherboard doesn't have over temperature protection and you run Prime 95 and the VRM hits 150 and the VRM dies, well, that's a problem, right? So that's where that's where the problems start up, really. But that doesn't mean you couldn't just slap a fan on it for the duration of, your Prime 95 stress test or whatever other stress test you're using. It's just, I like Prime 95 or Intel burn test. Those both run incredibly hot. If you're using something lighter, then you might not run into those issues, but, it depends. If you're running a lighter stress test, then, you won't run into those issues. But even if your lighter stress test is running into over temperature protection or getting the VRM really hot, then again, just smack a fan on it, finish your stress test, take the fan off. Because I understand that a lot of people don't like the aesthetic of a fan zip tied to the motherboard, or that it's really hard to get the fan in there. So in that case, you can put the system horizontal, and then the fan will stay in place just by gravity, basically. Both of those are basically a valid way of getting past the stress test portion, and then just never run anything intensive on the system. Though if you have an OT motherboard with over temperature protection, your only concern is that it's going to shut down or thermal throttle. If you don't have over temperature protection, well, that's when I would say don't overclock. Or if you're going to overclock that, then set up an overclock that under Prime 95 doesn't run the risk of, exceeding 125. Because there you're in the scenario where it's like that motherboard, like if something goes wrong and that motherboard is going to try run itself into the ground, there's nothing going to stop it, right? Like unless you notice that it's overheating through some monitoring software, assuming that even bloody works a lot of the time, right? Because a lot of the really, really cheap firecracker motherboards, they often don't even have the temperature sensors. That's why the freaking over temperature protection doesn't work. There's nothing to trigger it with, right? You can't protect yourself from overheating if you can't even measure what temperature you're at. So for those motherboards, it's like, yeah, that's what I definitely wouldn't overclock on. If you have a motherboard with OTP or something, then it's just inadequate for heavy, workloads, because you're going to shut down in them or thermal throttle in them. But it's not like you're going to be running the risk of the board blowing up. And then for an acceptable temperature, yeah, 110 is definitely an acceptable temperature for a VRM. 125 is the upper limit, I would say. And I would generally recommend you don't run at 125. But if you're hitting that, that's when I would start like trying to get the temperature down to 110. If you're running at 110, you're fine. If you're under 110, you're doing great. And if I get a motherboard and it's running at 110, then I'm going to complain about it because, especially if the heatsink looks like not a heatsink and more like a fashion accessory, I'm going to complain because last time I checked, heatsinks are there to remove heat, not to look pretty. So, you know, that's kind of my view on that. And admittedly, that does mean that I'm going to be overly critical of motherboards, but like if it doesn't change the manufacturing cost and it makes the motherboard a better motherboard, then, you know, that's my defense there. It's like, if the heatsink sucks at being a heatsink, it sucks at being a heatsink, and I'm not gonna ignore it just because the VRM isn't catching fire, right? So yeah, hopefully that covers everything you want to know about VRM temperatures. And it clears up some of the panic that I saw, like, well, some of some of the concerns that I've seen from people, because yeah, I read posts by people about like having Vega GPUs with the VRM at 107, and it's like, it's at 107, which is admittedly high, but it's not a problem. It's not going to die on you. At least not for the next 3 years. And maybe in 3 years, and it's not even going to die in the next 3 years. It's like at the end of those 3 years, you might notice that you can't overclock as far. But it might not even affect it that much, depending on, you know, if the manufacturer of the GPU went really overboard on how many capacitors there are, then at the end of those 3 years, those capacitors might be fine. Or if because also on GPUs, the capacitors actually get direct airflow. So I'd imagine that the temperature difference between the VRM MOSFETs proper and the capacitors themselves is actually going to be pretty significant, because when I do my motherboard testing, I don't have forced airflow over the VRM area, and the capacitors really act like heat sinks compared to the MOSFETs. The MOSFETs produce heat, and then whatever ends up getting to the capacitors is what takes the capacitor's temperature up. It's not the capacitors themselves getting hot. Even though they do produce small, negligible amount of heat. So, yeah. Hopefully that makes sense. And if it doesn't, then you can leave a comment down in the comments section below. You can like, you can share, and subscribe. You can share the video. You can also subscribe to the channel. And if you'd like to support what I do here with actually hardcore overclocking, then I have a Patreon, a PayPal, and t-shirts you can buy. There's a link to all of that down in the description below. And that's it for the video. I really do hope this made sense. And I might have made some mistakes because it's really long. And at this point, it's just like, And it is a kind of a complicated topic. But low hundreds are not reason for concern. So, on a VRM. So, yeah, that's it. Goodbye.